20 hours. That's how long it takes a single radio command to cross the gap between Earth and Voyager 2 right now. Not 20 hours to arrive and come back, 20 hours one way. Ask the spacecraft a question today, and you won't hear the answer until tomorrow, at the earliest, if it answers at all. Voyager 2 is about 21.35 billion kilometers from home. It left the protective bubble the sun builds around our entire solar system. Back in November 2018, becoming only the second human-made object to do it. And for years, the story we told ourselves about what was out there was comforting. Interstellar space, we assumed, would be quiet, empty. A slow, gentle fade from inside the sun's influence to outside it, like stepping from a warm room into a cool hallway. That is not what Voyager 2 found. What it found instead was a boundary that snapped shut behind it. A region thicker, stranger, and more turbulent than almost anyone expected. And in 2026, as engineers at NASA's Jet Propulsion Laboratory scrambled to squeeze a few more years of power out of a spacecraft older than most of its own mission team, that discovery started to look like more than science trivia. It started to look like a warning we weren't ready to hear, that the void beyond our sun isn't empty, and that our only working eyes out there are running out of time to keep watching it. This is the story of what Voyager 2 confirmed and why it matters more now than ever. To understand what changed, you first have to understand what everyone believed before Voyager 2 crossed over. Our sun isn't just a light in the sky, it's constantly exhaling, streaming out a thin wind of charged particles in every direction, fast enough and dense enough to inflate a bubble around the entire solar system. Scientists call that bubble the heliosphere. Inside it, the sun is in charge. Its wind pushes back against everything else in the galaxy, carving out a kind of pocket of home turf that stretches billions of kilometers past the orbit of Pluto. But the sun's wind doesn't blow forever. Eventually it runs out of force, collides with the thin gas drifting between the stars, and stalls. That stalling point is called the heliopause, the edge of the bubble, the last outpost of the sun's authority. Cross it, and you're no longer in the solar system in any meaningful sense. You're in the galaxy itself, swimming in material that isn't from our sun at all, some of it older than the sun by billions of years. For decades, the leading assumption was that this transition would be gradual, a thinning out. Solar wind fading, interstellar material rising, the two blending together the way a river blends into the sea. Picture it that way for a moment, because the river is the analogy scientists themselves reached for. A river doesn't stop at a line. It slows, spreads, mixes with the ocean over a wide, indistinct zone until you can no longer say exactly where the river ends and the sea begins. That was the mental model. Soft edges. No dramatic threshold to cross, just a long, quiet dissolve. The river analogy breaks down almost immediately once you look at what Voyager 2 actually measured, and that breakdown is the whole point of the story. Real boundaries in nature are often messier than the tidy pictures we draw of them, and the heliopause, it turns out, behaves less like a river meeting the sea and more like a held-together membrane, pressurized from the inside, resisting the outside world right up until it doesn't. Voyager 1 punched through first in 2012, and its instruments hinted the crossing wasn't as smooth as expected. But Voyager 1's plasma detector, the tool best suited to directly measure what kind of charged particles surrounded it, had stopped working decades earlier. Scientists were reading the boundary secondhand, through indirect measurements and clever inference. Voyager 2 was different. Its plasma instrument still worked. When it crossed the heliopause in November 2018, it became the first spacecraft in history to directly sample the transition from solar wind to interstellar plasma in real time, with a fully functioning instrument built for exactly that job. And the readings didn't look like a gradual fade at all. The data came back in pieces, and by 2019 it had been assembled into 5 separate papers published in the journal Nature Astronomy. Together, they described something researchers hadn't fully anticipated. The boundary wasn't a soft gradient, it was sharp, almost like a wall. Density readings jumped, instead of the solar wind thinning out gradually into the interstellar medium the way steam disperses. Into open air, Voyager 2's instruments recorded a comparatively abrupt shift. Solar plasma essentially cut off, interstellar plasma essentially cut in, over a much shorter distance than models had predicted. Think about what that means physically. The heliosphere isn't fading into the galaxy. It's holding a shape, pushing back against the interstellar wind hard enough to maintain a defined edge, like a bubble under real pressure rather than a puff of smoke dissolving into a room. Later analysis, combining both Voyager 1 and Voyager 2's crossing points, suggested that shape wasn't even symmetrical. The heliosphere appeared to be lopsided, blunter and more compressed in some directions, stretched longer in others, something closer to a dented, blunt bullet than a perfect sphere. That alone reframed something people had quietly assumed was settled. The sun's bubble isn't a passive, symmetrical shield drifting through empty space. It's a structure under constant pressure, being shoved and reshaped by whatever the galaxy is throwing at it from the outside. And whatever the galaxy is throwing at it turned out to be the second surprise. Before Voyager 2 crossed over, researchers expected interstellar space near the heliopause to be colder, and the magnetic field there to point in a noticeably different direction than the field inside the bubble. Evidence that the two environments were truly separate, unconnected systems. Instead, Voyager 2's magnetometer picked something up that nobody had a clean explanation for. The magnetic field just outside the heliopause was closely aligned with the magnetic field just inside it. Nearly parallel, not sharply divided. That's the kind of detail that sounds small until you sit with it. If the two fields are that closely aligned, it suggests the heliosphere isn't a sealed container the way a lot of popular illustrations imply. It suggests the boundary is porous, that the sun's magnetic influence is, in some way, researchers are still working out, threading through into the interstellar medium, or that the interstellar magnetic field is bending itself around the heliosphere in a way current models don't fully capture. Either way, the same conclusion kept surfacing across all 5 studies. The edge of our solar system is not a clean line on a diagram. It's a contested dynamic frontier, still being fought over by 2 different physical environments, and Voyager 2 flew straight through the middle of that fight. Here's where the story usually pauses to recap. So let's do that quickly, because what comes next builds directly on it. What we know, the heliopause is a sharp, not gradual boundary. The heliosphere's shape is asymmetrical, shoved and dented by pressure from outside. And the magnetic fields on either side of that boundary are more connected than anyone predicted. What we didn't know yet, in 2018, was what any of that meant for the region beyond the boundary, the true interstellar medium, the material Voyager 2 would keep flying through for years afterward. That's where the story gets less comfortable. Related work using Voyager 1's older data, published in the astrophysical journal Letters, tracked something else. The density of the interstellar plasma isn't uniform out there either. Researchers detected a pressure pulse, a kind of shockwave rippling through the interstellar medium, that temporarily spiked the plasma density Voyager 1 was flying through, before the density settled into a new, elevated baseline. In plain terms, the space between the stars isn't the static vacuum most of us picture. It has weather, pressure fronts move through it, shocks propagate across it. Something out there is disturbing it, and the leading interpretation is that our own sun's activity, solar outbursts, the 11-year solar cycle, is still shoving material outward, generating ripples that reach the spacecraft even after they've left the bubble behind. That is the part that quietly undercuts the old comfortable picture. Interstellar space isn't a calm, silent gap between islands of activity. It's connected to what the sun is doing, disturbed by it, and shaped by forces from both directions at once. Voyager 2 isn't sailing into stillness. It's sailing into a region that's still turbulent, still reactive, still being pushed around by 2 competing systems. For anyone who assumed beyond the sun's reach meant beyond anything's reach, that assumption doesn't hold up under the data. There's a practical dimension to this too, one that goes beyond pure curiosity about the boundary of our solar system. Inside the heliosphere, the sun's magnetic field and solar wind act as a kind of shield, deflecting a large share of the high-energy cosmic rays that constantly stream in from the rest of the galaxy. Voyager 2's instruments recorded a measurable jump in cosmic ray intensity right as it crossed the heliopause. Direct, physical proof that the shield we live inside is doing real work, and that the environment beyond it is measurably more radiation-heavy. T-hat single reading matters for anyone thinking seriously about long-duration missions beyond the solar system someday. The protection spacecraft and astronauts currently take for granted inside the heliosphere isn't guaranteed to extend very far past its edge. Now, for the second half of what makes this story urgent instead of just interesting, Voyager 2 is not healthy. It is a machine from 1977, running on a radioisotope thermoelectric generator that loses a small amount of usable power every single year as its plutonium fuel decays. T-hat decline has been relentless and mathematically predictable since launch. Engineers have spent the last decade doing something that sounds almost undignified for a spacecraft this historic, turning things off, one instrument at a time, just to keep the lights on for the instruments that remain. The plasma instrument that made the 2018 discovery possible, the magnetometer that caught the aligned fields, the cosmic ray detector. Each one draws power the spacecraft increasingly can't spare. Mission planners have had to choose, instrument by instrument, what stays awake and what goes silent, permanently, because nothing about Voyager 2 can ever be repaired. Every command takes roughly 20 hours to arrive and another 20 to confirm it worked, which means every decision about this spacecraft is made blind, in a conversation with a 40-hour delay. In 2026, the Voyager team found a way to buy a little more time. Engineers identified an unused safety reserve, power that had been set aside decades ago, purely as a precaution. and worked out how to redirect it into keeping instruments running rather than sitting unused. It wasn't a fix in the sense of solving the underlying problem. Voyager 2's power will still run out. It bought the mission more months, possibly a few more years, of a spacecraft that was never designed to survive this long in the first place. That single fact reframes everything the science has told us so far. We now know the edge of our solar system is sharper, stranger, and more contested than we assumed. We now know the space beyond it is turbulent, not calm. And we know that the only instrument-equipped spacecraft capable of directly measuring any of it, Voyager 1 and Voyager 2, are both dying on a schedule nobody can extend indefinitely. There is no second Voyager waiting to launch. The Interstellar Mapping and Acceleration Probe, which reached orbit in 2025, is a remarkable tool for studying the heliosphere from a distance, from just inside the boundary looking out. But it is not a replacement for a spacecraft physically embedded in the interstellar medium itself, radioing back direct measurements from a place nothing else has ever touched. When Voyager 2's last instrument goes dark, humanity loses its only direct sensor in that specific environment, and there is no engineering plan on Earth today that puts another one there within our lifetimes. Researchers have discussed in broad terms a future interstellar probe designed from the ground up to push past the heliopause faster and further than Voyager ever could. But a mission like that exists today only as a concept on paper, years from a funding decision, decades from launch, and even longer from reaching the boundary. Voyager 2 crossed back in 2018. However that timeline plays out, it does nothing to change the math on the spacecraft we already have in flight right now, quietly running out of watts 1 year at a time. So what did Voyager 2 actually confirm? The thing we all feared, if we're being honest about the phrase? Not a monster, not a threat racing toward Earth. Something quieter and, in its own way, more unsettling. That the boundary of our solar system is not a soft, forgiving edge fading gently into peaceful darkness. It's a battlefield holding its shape under pressure. And beyond it, space is not empty and inert. It's active, disturbed, still connected to a sun 90-plus astronomical units away, by mechanisms scientists are still working to fully explain. We feared, quietly, that we understood less about our own cosmic backyard than we let ourselves admit. Voyager 2 confirmed it, and we feared that the window to actually go check, to fly something out there and ask it, directly, was closing faster than any of us wanted to accept. Voyager 2 is confirming that too, one conserved watt at a time, with every year that passes and every instrument that has to be switched off for good. The spacecraft that answered our oldest question about where the solar system ends is now, itself, running out of time to answer the questions that discovery opened up. Somewhere, out past 21 billion kilometers, a machine built the same year as the first Star Wars film is still transmitting, faintly, patiently, 20 hours at a time, from a region of space we only started to understand because it was brave or stubborn enough to fly straight through the wall nobody knew was there. If you had to guess how many more years Voyager 2 has left before its last instrument finally goes silent, what would you put money on? Put your number in the comments, and when NASA finally confirms it, come back and see who was closest.